Hey, and welcome to Programmatic Sideways Friction. What we're going to be doing in this video is to apply some friction sideways so that as I turn, I can actually turn without slipping sideways. Pretty cool, hey? Let's do it. By the way, the AI tanks will have to do the same thing, of course, because they use the same control API as we do. So just before we start this one, I want to fix a bug. If I open, and I'm not going to, my tank player controller blueprint, it's actually going to cause a hard crash. If you attach the debugger and find out why, I'll show you why, and let's just mitigate this issue for now so that you don't have this hanging over you. Look in your tank player controller CPP code. And then if we have a look at where we aim towards the crosshair, we are assuming here that we actually have a possessed pawn right now. So what we want to say is if not get pawn, and I don't mind doing this again, it's a very inlineable, very optimizable operation. If not get pawn, then I simply want to return. And then this is, for example, if not possessing. Now we don't use an ensure here because it's a runtime. At runtime, we may not be possessing a tank, the player controller. Maybe our tank's died or something. So it's perfectly reasonable to just exit if we're not possessing. If you do that, just add that line of code there to your tank player controller, and we recompile. Then that will make sure that at times like this, like right now, if I click play, if I try and open this tank player controller, because we're not possessing a tank right now, as a player, it would crash, but now it won't crash because that protection is in place, okay? And aiming will still be working, which is good. Just going to check for this green and then amber. Okay, now let's move on and make this friction work. So what's happening at the moment is the tank is sliding sideways because there's no reason for the physics engine to apply any sort of asymmetric friction. Friction is the same forward, backwards, left and right. What we want to do is apply a sideways force that is exactly the right amount of force to stop the tank moving sideways at all. Tanks don't really do moving sideways apart from perhaps on some very slippy terrain. So it's this type of movement we want to stop. How are we going to do that? Well, let's go into our tanktrack.cpp and take a look. We're firstly going to need a constructor and a tick. So, well, because in order to make it tick, you have to put the constructor in place. So let's just quickly do that. tanktrack is what we do for the constructor definition. tanktrack, strange naming with the constructors here. And then we need this begin play boolean. What was it? Let's look in the tank aiming component. Primary component tick.b can ever tick equals true, which we've done before. Perfect. So that is now provided that we have a constructor declared, which I'll do. I like to do it in the private section. It works, as I say, because of Unreal Magic. tanktrack is the name of the method, the same as the class name. That's how we do constructors. Okay, fantastic. Now, how am I going to get the ticking working? Well, what type of class is this? It's a static mesh component. Let's just have a look in the class hierarchy and find out what a static mesh component is. Static mesh component is a type of mesh component, is a type of primitive component, is a scene component. Finally, is an actor component. So, because it is also a child of actor component, just like our tank aiming component was, if you remember, we can use the same signature as we had in the tank aiming component. So here it is. We just need to modify it slightly for the new class. So I'm going to put that in. tanktrack, get rid of all the code.
Sam here with a quick edit. I wanted to point out that we're going to forget to add the super tick component into this method call, which means that the superclass's tick component doesn't get called. Now, it's okay in this case because the tick component essentially just called the blueprint tick event. And if you have no blueprints deriving, as we don't have here, no tick event there, then we won't see any problems. But in general, it is good practice to add your super tick component here. And if you do that, it's not going to change the behavior, and you should probably do it for good habit. Thanks to Eric in the Q&A for pointing that out.
Now, what else do I need? Void. I need no T's in there. No override on the end. That's great. So that's nearly there. I better just check its log that it's working. Log temp warning. Text, getting bored of typing this, track ticking. Okay, doesn't matter that I spelt it wrong in this case because it's going to be a very temporary message. Let's put this ticking here inside the declaration with an override It's just moving code around and getting the ticking working again. And then we take all this stuff off the front here, the class name, virtual needs to go in, and let's just test with ticking. So, sorry about a couple of minutes worth of housekeeping in order to make that work, but it's good to revise how to put the ticking back, and hopefully you stopped and did that yourself. So sometimes when you're watching these videos, if you think, oh, I could do that, I don't need to sit and watch it, don't wait for me to tell you to do a challenge yourself, just do it yourself. There you go, tank tickling or whatever it says. That's good. So we are ticking, that's fantastic. All right, so what are we going to do when we're ticking? How are we going to apply a sideways force? Well, the general recipe I'll help you with is as follows. We need to calculate the slippage speed, not velocity, speed, it's just a number, which is the sideways component of the speed. We'll use a cross product for that. Then we work out the required acceleration, this frame, to correct. So if we're moving sideways at 10 centimeters a second, then this frame in this delta time, we're going to need a certain amount of acceleration to fix that velocity back down to 0 sideways. Then we calculate and apply sideways force. Remember, F equals ma. We have the mass of the tank. We have the acceleration just above. We've just calculated it, so we apply a sideways force. So let's start off with calculating the slippage speed. I'm going to use auto because I like it. Slippage speed equals... Well, what is the slippage speed? Let's have a look. I'm going to challenge you to make it. It's the component of the speed in the tank right direction. We're just choosing that as a sideways direction. If there's no slippage, this should be 0. And if it's sliding entirely sideways, the slippage speed will be the same as the speed of the tank. In general, use the cosine of the angle between the velocity of the tank, whichever direction it's actually going in, and the sideways right vector. So if it is going perfectly sideways, the cosine between those two angles is 1, because the cosine of 0 is 1, and you get the full speed. If it's going forward, then the angle is 90 degrees, cosine of 90 is 0, so you get a 0, okay? And as a hint for you, well, it's not really a hint, it's a strong suggestion, use F vector dot product between the velocity of the tank or the component. You may want to use get component velocity and the tank right vector, and there's a get right vector method. So have a go. Just work out this slippage speed, make sure you understand what you're doing, and I'll see you in a moment. Okay, welcome back. So this slippage speed is going to be the F vector static method called dot product between the what? Well, we can get the right vector. Before we go any further with that, let's just check in our tank blueprint that the tank track has a forward vector the same as the tank, an X. The red arrow on the tank itself, or on, say, no, we need to look at the tank itself. Well, this is in the frame of the tank. X is forward. Let's just check that the track has that same forward. It does. Okay, that's good. So then we are getting the right vector of the component, which is the tank track, and we're going to cross product that with or dot product with it rather, and it doesn't matter which order we do a dot product in, with the get component velocity, which is going to tell us the velocity of this component itself, which is the track. And hopefully, unless the tank is falling apart, then the component velocity will be the same as the tank velocity. And we're not going to be dealing with the destruction of the tank in this section. Okay, so that is the slippage speed. Now we need to work out the required acceleration. I don't need that comment, but we do need the acceleration. So auto, I'm going to call it correction or correcting acceleration equals what? Well, acceleration is speed over time, isn't it? So meters per second, acceleration is speed over time, 0 to 60. How speed is 60 over time. Tells you how quickly you're getting to 60. So we're going to take this slippage speed, and we're going to divide it by the delta time, which is available here as a parameter. And that tells us how much acceleration we need in this frame. Now, which direction is that acceleration in? Well, we need an acceleration which is actually a vector, so we multiply it by this get right vector again. You could store that as a variable, local variable, if you wanted to. We're nearly there, but we don't want to apply the acceleration in the direction that we're slipping. We want to apply it in the opposite direction to what we're slipping in. Okay, so we put a minus in here. the opposite direction to that we're slipping in. Okay, so that's the acceleration this frame to correct. And then we are going to calculate and apply a sideways friction. And I don't need the word for, which is F equals ma. So how do we work out the sideways friction? Well, I think I'll do it in two stages. I'm going to make a correction force. What is that equal to? Well, force is mass times acceleration. So we need to get tank root. So how do we get the tank root component? We are a tank track. I need to get the mass from this tank at the top here. If you remember, it's this tank here that actually has a mass on it in kilos. This guy here, it's a static mesh component, which is the root of this hierarchy. How do I get that from the tank track? Well, let's try doing that before we even try and work out the correction force. We can say auto. Then we can say, well, how are we going to get this tank root? Well, we need to get the owner for a start. What does that do? That goes up and gets this guy here from the track. So once we've got the owner, we look through that pointer, provided that we can find an owner, of course. We may want to check that, but to be honest, the tank is pre-composed. I'm pretty safe leaving that for the moment. Then we get the root component. We've done this type of thing before, which is where we go down and find the tank root component there. And let's see what type that is. If I just get owner, get root component, let's see what we end up with. Provided I have my semicolons in the right place, let's just see what comes out of here. Once it catches up, we'll see what this auto... I haven't given it a name, of course. So I'm going to call it tank root. Auto tank root is get owner, get root component. What comes out of that? It is a U-scene component pointer, which is this guy here. Now let's look at the class hierarchy again. Scene component is a type of actor component, and then where does static mesh component comes into this? A static mesh component is a specialization of a scene component, but we need the static mesh component in order to actually get from the tank the mass, because if we look on the tank blueprint, it's the fact that it's a static mesh that is giving us, and this physics property that is giving us a mass. So what we need to do with this tank root is we need to cast it to a U-static mesh component in order to be able to get the properties that we want from it. So we cast to U-static mesh component once we go and find this object here. We go get it as a static mesh component. All right, that allows us to simply talk about the tank root. Then we can just say get mass. Like that. It's a method that's provided for us. If we multiply that mass by the correction acceleration that we've worked out, mass times acceleration, is nearly force. The only thing is we need to divide by 2 because there are 2 tracks. Okay, so that is the correction force. Now we need to do is apply it. So we already have this tank root thing. And you'll find that when you look through the pointer of the tank root, we can just add force. That's why we had to cast it. It gives us all these methods, and it's the correction force that we add. So a bit physicsy for you there, but what we've done is worked out the slippage speed, worked out the required acceleration, and calculated and applied a sideways friction, precisely as we pseudo-coded. Let's go ahead and compile this and see if it works. By the way, when I'll compile, then I'll give you the by the way. By the way, this tank root, we could go and cache that state. We could do that at begin play, and then we could protect against it and check it. But why cache it at the moment until a performance profiler tells us there's a performance problem? Let's not bother caching it. Let's just focus on simple physics. Okay, using the left stick here. That is looking a lot better. Now, the very cool thing about the architecture that we've set up is watch the AI tanks now. Apart from these bugs with them hitting the ground, notice that they then have to move. One of them's not moving, actually, so let me refresh the guy who's not moving. I think it was him. By refreshing him, I need to just drop a new blueprint in the game. But watch how they move. They have to move according to the same physics, because they're using the same API as I am. Oh dear, we have this significant ground problem. So that's going to have to be a thing we look at very shortly now. But what I want you to notice is that all the tanks now have sideways friction. Totally different movement for all of us. So that is pretty awesome. So congratulations on getting that far with the sideways friction, and I will see you in the next video.